When we look at how modern medicine tracks a patient's stability, there is just this immense reliance on the intake and output chart.
Oh, absolutely. The classic I&O.
Right. And it looks like this perfectly balanced accounting ledger, at the end of a nursing shift. You have this meticulous log of every single milliliter of IV fluid or water the patient consumed, measured right up against every milliliter of urine or drainage that left the body.
Yeah, it's very neat, very tidy.
Exactly. And the fundamental assumption here is that if those two columns match, well, the patient is perfectly hydrated and physiologically stable.
Which is, I mean, it provides a really comforting illusion of control, right? We basically try to map complex human physiology onto this super basic thermodynamic principle of, input equaling output.
But I'm guessing the clinical reality is a bit more deceptive than that.
Far more deceptive, yeah. A patient can have a flawlessly matched chart on paper where the total volume of water in their body is technically totally normal, but they are simultaneously experiencing a lethal fluid crisis.
Wow, wait, so how does that happen?
Well, the critical factor we constantly misinterpret isn't the total volume of water, it's the geographic location of that water within the microscopic compartments of the body.
Okay, and that spatial distribution is exactly our target for this deep dive. We are unpacking the true architecture of fluid balance today.
Right. It's fascinating stuff.
We're going to examine the biological mechanisms that drive water into hidden tissue compartments, which is often called third spacing. And we'll also look at why the reflexive medical instinct to just give IV fluids to a shock patient can sometimes trigger catastrophic organ failure.
Yeah, which goes against decades of medical training, by the way.
Right. And we'll also talk about how the biological mechanisms governing a trauma patient in the ICU are actually identical to the ones causing marathon runners to inadvertently drown their own brain cells.
It is all connected. So to really dismantle that reliance on the intake and output ledger, we basically have to start by mapping where the fluid actually lives.
Okay, let's map it.
So we frequently hear this baseline statistic that the average adult body is roughly 60% water.
Right, yeah, the classic science class trivia fact.
Exactly. Clinically, though, that total percentage is almost irrelevant. It really comes down to how that volume is partitioned.
Because we tend to visualize the body as a single vessel,
Sure.
just as giant water balloon of sloshing fluid. But the partitioning is actually highly segregated.
Very much so.
Like, of that total body water, 2/3 is entirely locked away inside the intracellular fluid compartment. It's just spoken for, just maintaining the function of your individual cells.
Right, which leaves only 1/3 of your total water in the extracellular fluid compartment. And this right here is the pivot point where our intuitive understanding usually just completely fails.
Also,
Well, of that extracellular fluid, the water outside the cells, only about 1/4 is actually circulating inside your blood vessels as plasma.
boy, only a quarter.
It's just a quarter. The remaining 3/4 is what we call interstitial fluid, which is basically the water bathing the tissues and filling all those microscopic gaps between the cells.
Okay, so if we map this onto a visual analogy for you listening, imagine your body is a house.
I love this analogy.
Right. So the plasma, the fluid inside the blood vessels, is the plumbing system. But the vast majority of the water in this house isn't in the pipes at all.
Not at all.
It's sitting locked inside the individual rooms, which are the cells,
Yeah.
or it is literally soaking into the drywall and the insulation, which represents that interstitial fluid you just mentioned.
And the massive clinical challenge here is that doctors and nurses can only easily access and measure the plumbing. When you take a blood pressure or draw labs or, measure urine output, you are only interacting with the plasma. You're staring at the pipes, completely blind to what is happening inside the walls.
That's wild. And the recognition of these distinct environments actually dates back to Claude Bernard in the 19th century, right? With his concept of the milieu interieur.
Yes, the internal environment.
He proposed that our cells don't actually interact with the external world. They survive in this highly defended sort of primordial internal ocean.
But translating that concept into actual bedside medicine didn't really happen until James L. Gamble's work in the mid-20th century.
Right, Campbell.
Yeah, he was a Harvard pediatrician, and he was confronting this massive pediatric mortality rate from diarrheal dehydration. Prior to his work, the standard of care was basically just pouring uncalibrated saline solutions into these kids.
We were just topping off the tank.
Exactly. They assumed fluid was just fluid. But Gamble recognized that the body's compartments rely on highly specific electrical and chemical gradients.
So he mapped out the precise concentrations of like sodium, potassium, and chloride in the different fluid compartments.
Right, and he created these visual bar charts called gamblegrams.
I love that name.
It's great, right? And it shifted medicine from blindly topping off the tank to precisely replacing the specific electrolytes a patient lost. So if a child lost bicarbonate and potassium, Gamble's charts allowed doctors to formulate a fluid that replaced those exact molecules.
Just to restore the osmotic pressure.
Exactly. And those osmotic pressures are what keep the water in the correct compartments.
But Gamble's work mostly addressed fluid that actually leads the body, like through diarrhea. The map gets terrifyingly complicated when the fluid doesn't leave the body, but it just escapes the plumbing.
Yes. Welcome to the third space.
The phantom zone.
Basically, yeah. So Francis D. Moore, a surgeon who was analyzing trauma patients from World War II and the Korean War, he noticed this massive discrepancy.
What were the soldiers showing up with?
Well, they were arriving with severe injuries, their blood pressure was crashing, and their urine output had just completely stopped. They looked profoundly dehydrated.
But let me guess, the visible blood loss didn't match the severity of the shock.
Exactly. The surgeons would calculate the blood loss, and it just didn't add up. The soldiers were missing massive volumes of fluid that couldn't be accounted for on any external chart.
So where was it going?
Moore figured out that the trauma had triggered a systemic inflammatory response. The capillaries, the tiny porous pipes of the circulatory system, had become hyperpermeable.
They got leaky.
Super leaky. The fluid was leaking out of the intravascular space and pooling into the injured soft tissues, the bowel walls, the abdominal cavity.
Wow. So the water hadn't actually left the soldier's body?
Right. It was still inside them, but it was entirely lost to the circulation. It was sequestered in this non-functional third space.
Which just completely invalidates the standard intake and output chart. The nursing ledger can't measure fluid that's hiding in the body's drywall.
It absolutely cannot. And to make it worse, standard charts routinely ignore insensible losses.
Like breathing and sweating.
Yeah. An average resting adult breathes out and sweats roughly 800 to 1,000 milliliters of water vapor a day.
That's a whole liter.
Right. And if you have a patient on a ventilator or someone with a high fever, those unmeasured losses just skyrocket.
Which is why the daily weight of a patient is such a far more rigorous proxy for fluid balance than any written ledger.
Yes. The physics are absolute. 1 liter of retained fluid has a mass of exactly 1 kilogram.
So if a patient's intake and output chart claims they're perfectly balanced, but the scale shows they gained, say, 3 kilograms overnight.
You know, with absolute certainty that 3 liters of fluid have leaked out of their plumbing and are actively third spacing into their tissues.
That is just wild. And to visualize the sheer scale of this third spacing, we really should look at the protocols for severe burn victims.
Oh, yeah. The fluid shifts there are unimaginable.
Right, because when a patient suffers a major thermal injury, the capillary leak is catastrophic. So to prevent the plumbing from running completely dry, burn units use the Parkland formula to calculate resuscitation fluids.
And it is a lot of fluid.
The math is 4 milliliters of fluid multiplied by the patient's weight in kilograms, multiplied by the percentage of their body surface area that's burned.
So if we run those numbers for a standard 70-kilogram adult with a 40% total body surface area burn, which, to be clear, is an incredibly severe, life-threatening injury.
The result is staggering. 4 times 70 times 40. That is 11,200 milliliters.
Yeah.
11.2 liters of 5E fluid required in just the first 24 hours, with half of that volume mandated in just the first 8 hours.
It's massive. The clinical team is effectively forced to flood the patient's circulatory system just to maintain enough pressure to perfuse the brain and the kidneys.
Even though they fully know that a massive percentage of that 11 liters is going to leak straight out of the damaged capillaries.
Oh, completely. It's going to cause the patient's entire body to swell to almost unrecognizable proportions.
Okay, I have to challenge the mechanics of that treatment protocol for a second.
Go for it.
If I'm the attending physician, and I see a patient whose tissues are actively ballooning with liters of trapped third space fluid, my mechanical instinct is to just drain the system.
Sure, that makes intuitive sense.
Right. I'd want to give them a powerful loop diuretic, like furosemide, to force the body to excrete that excess water and relieve the swelling.
And administering a diuretic in the acute phase of a third space crisis is actually one of the most lethal conceptual errors a clinician can make.
Wait, really? Why?
It comes back to our map of the fluid compartments. Diuretics act specifically on the kidneys. and the kidneys are just a filter attached to the plumbing.
Ah, so they only have access to the intravascular volume.
Exactly. The fluid currently circulating inside the blood vessels. The kidneys have no physical mechanism to reach into the interstitial tissue and pull water out of the walls.
So if you push a diuretic.
The kidneys will aggressively filter and excrete whatever volume is currently in the plasma. But in a burn or trauma patient, the plasma volume is already dangerously depleted. It's all leaking into the tissues.
So the diuretic would just instantly drain the last remaining fluid from the pipes.
Yes, causing a catastrophic drop in blood pressure and inducing multi-organ failure. And the massive tissue swelling won't even go down because that fluid is sequestered away from the kidney's reach anyway.
Wow. So the only viable mechanism for removing that fluid is just time.
Basically, time and healing. The underlying inflammation has to resolve. Once the capillary leak seals, which is usually around day 3 to 5, the hydrostatic and osmotic pressures naturally pull that trapped fluid back into the blood vessels.
And only then can the kidneys filter it out.
Precisely. And waiting for the capillaries to seal brings us to probably the most contentious debate in modern critical care right now, the liberal versus restrictive fluid strategy.
Because for nearly a century, medical dogma basically dictated that if a patient had low blood pressure from sepsis or trauma, the immediate reflex was to administer a huge IV fluid bolus.
Right. Fill the pipes. Increase cardiac output.
And this was heavily based on the Starling equation from 1896, right, which modeled capillary exchange purely as a balance of physical hydrostatic pressure pushing fluid out and the oncotic pressure of plasma proteins pulling it back in.
Yeah, it treated the blood vessel like it was just a passive, semi-permeable membrane, like a coffee filter.
But modern vascular physiology has identified a microscopic structure that completely breaks that old Starling model.
The endothelial glycocalyx.
The what?
Glycocalyx. It is this microscopic, gel-like meshwork of glycoproteins and proteoglycans that coats the inner lining of every single blood vessel in your body.
Oh, wow. So it functions like a biological Teflon coating.
Exactly like Teflon. It isn't just a passive barrier. It actively repels red blood cells, it houses regulatory enzymes, and most importantly, it traps plasma proteins to maintain the osmotic gradient that keeps water inside the vessel.
So what happens to this Teflon coating when a patient develops sepsis?
Well, the immune system releases this massive storm of inflammatory cytokines and enzymes. And these enzymes literally chew up and degrade that delicate sugar protein layer.
Just destroys it.
Yeah, and the body actually does this intentionally to allow white blood cells to slip out of the bloodstream and attack the infection in the tissues.
Right, but the biological cost of stripping that Teflon coating is that the plumbing completely loses its structural integrity.
Once the glycocalyx is degraded, the capillaries aren't just leaky, they are functionally shattered.
Which completely reframes our approach to resuscitation.
Completely. Because if the vessel lining is destroyed, pushing a rapid bolus of IV fluid doesn't meaningfully increase blood pressure. The fluid simply bypasses that degraded barrier and floods straight into the interstitial space.
And we actually have massive clinical data proving how lethal this traditional fluid reflex can be, like the FEAST trial.
Oh, yes. Fluid expansion as supportive therapy, published in 2011.
Right, where researchers studied over 3,000 critically ill children with severe febrile illnesses across sub-Saharan Africa. And the absolute gold standard protocol for a child in shock was to administer a rapid fluid bolus.
Because the underlying assumption was that the bolus would restore the volume in the pipes and improve tissue oxygenation.
But the trial was halted early, wasn't it?
It was, because the results were absolutely devastating. The children randomized to receive the standard fluid boluses had a 3.3% higher absolute mortality rate compared to the control group that received no bolus at all.
Wait, really? Giving the standard, trusted treatment actually pushed fluid through those damaged glycocalyx barriers into their lungs, causing pulmonary edema, and into their brains, causing cerebral edema.
Yes. The textbook intervention accelerated their death. It was a massive, paradigm-shifting realization for the medical community.
That is deeply unsettling. But it also echoes the findings of the 2004 SAFE study, right?
Right, in Australia and New Zealand. For decades, ICUs spent insane amounts of money administering albumin, which is this large, expensive human protein, instead of just cheap saline.
Because the theory was that the massive albumin molecules wouldn't be able to leak out of the capillary.
Exactly. They thought it would hold the water in the pipes via oncotic pressure.
But the SAFE study proved there was zero overall mortality benefit to albumin over standard saline.
None at all. Because if the glycocalyx is destroyed, Even massive proteins will hemorrhage out into the third space and they drag the water right along with them. The barrier itself is the critical failure point.
But here's the thing, the degradation of those vascular walls and the shifting of fluid compartments, that's not just a phenomenon restricted to trauma bays and ICUs, right?
Oh, not at all. The exact same hormonal triggers that mismanage fluid distribution during a severe infection, they can be hijacked during everyday activities.
Which bridges the gap to sports physiology. Because we see catastrophic fluid shifts occurring in amateur athletes who are literally just adhering to what they think are healthy hydration guidelines.
Yes. And the primary culprit here is antidiuretic hormone, or ADH.
Okay, so ADH is secreted by the pituitary gland, and its primary function is to instruct the kidneys to conserve water.
Right. It does that by inserting water channels, called aquaporins, into the kidney ducts. And your body naturally releases massive surges of ADH when you are under physical stress, when you are experiencing pain, or when your blood volume slightly drops from sweating.
Which perfectly describes the physiological state of a person running a marathon.
Perfectly.
So during the 2002 Boston Marathon, there was this study by Dr. Christopher Almond. His team drew blood from nearly 500 runners at the finish line. And he discovered that 13% of them were suffering from hyponatremia.
Which is dangerously low concentrations of sodium in the blood.
But crucially, they didn't develop hyponatremia because they sweat out all their body salt.
No, they developed it because they drank too much plain water. They basically followed the pervasive advice to drink at every single hydration station.
And because their systems were flooded with that stress hormone, ADH, their kidneys were chemically blocked from excreting that heavy water load.
Exactly. So the plain water had nowhere to go except into the bloodstream, where it massively diluted the existing sodium.
And this is where the physics of osmosis become incredibly deadly, because the blood plasma becomes hypotonic, meaning it's extremely watered down compared to the fluid inside the body's cells.
Right. And to equalize that pressure, that excess water is forcefully driven out of the plumbing and across the cell membranes,
rushing into the intracellular compartment, so the cells physically swell up.
And while a swollen muscle cell is painful, a swollen brain cell is life-threatening.
Because the skull is a rigid, fixed vault. It can't expand.
Right. So as the brain cells absorb this hypotonic water, they expand, increasing intracranial pressure. This is early hyponatremic encephalopathy.
And the external symptoms of this brain swelling, nausea, extreme fatigue, confusion, collapsing. The tragic overlap here is that these symptoms flawlessly mimic the signs of severe dehydration.
It looks exactly the same. So when a runner collapses at the finish line exhibiting confusion and cramping, the immediate instinct of a well-meaning bystander or a medical volunteer is to assume, oh, they're dehydrated.
So they hand them a bottle of water. Or worse, a medic hooks them up to an IV bag of hypotonic fluid.
Which instantly exacerbates the osmotic gradient. It pushes even more water into the brain, herniating the brainstem and literally killing the athlete.
It's terrifying. Fatalities at major marathons have been directly caused by this precise sequence of well-intentioned but physiologically backward medical care.
It really emphasizes why understanding these mechanisms is so crucial. But on the flip side, mastering these fluid shifts has actively engineered some of the most profound medical advancements in history.
Like oral rehydration therapy, or ORT.
Yes. Back in the 1970s, researchers investigating cholera and severe diarrheal diseases, they mapped out this specific protein embedded in the intestinal lining.
The sodium glucose cotransporter, right? SGLT1.
Right. And this transporter acts as a molecular pump. It couples the transport of one glucose molecule with two sodium ions.
So if a patient just drinks plain water, it moves sluggishly across the inflamed intestinal wall.
And if they drink purely salty water, the sodium remains in the gut and actually draws more water out of the body, worsening the diarrhea.
But if you create a solution with a highly specific molar ratio of sodium and glucose,
the SGLT1 transporter engages. It actively pulls the salt and sugar across the intestinal epithelium.
And that localized movement creates a powerful osmotic gradient that physically drags massive amounts of water along with it, straight into the bloodstream.
It's brilliant. This simple, hyper-calibrated mixture of sugar, salt, and water bypasses the need for intravenous fluids entirely. It has saved tens of millions of lives globally.
which is amazing. Yet we see this massive disconnect in the modern commercialization of hydration today.
Oh, don't even get me started on the IV drip bars.
Right. We have these wellness clinics in strip malls, heavily marketing intravenous fluid bags to the general public for like hangovers or general fatigue.
People are paying out of pocket to bypass their perfectly functioning, highly evolved GI tracts and SGLT1 transporters. They're forcing uncalibrated fluids directly into their intravascular plumbing, completely ignoring the complex hydrostatic pressures and glycocalyx barriers we've just spent all this time talking about.
It trivializes a really fragile medical intervention.
Yeah.
And honestly, it assumes an infinite abundance of supplies, which we know is a deeply flawed premise.
No, definitely.
I mean, the fragility of our reliance on manufactured fluid compartments became terrifyingly clear in late 2024.
With Hurricane Helene.
Yeah. Hurricane Helene caused catastrophic flooding in North Carolina, directly incapacitating a massive manufacturing plant that produced a huge percentage of the nation's IV fluids.
Literally overnight, the abstract physiology of fluid balance became a brutal supply chain crisis.
Hospitals nationwide were forced to instantly ration IV fluids.
Yeah.
Bedside clinicians had to delay elective surgeries and rethink every single milliliter of fluid they administered.
It was a very stark reminder that a bag of normal saline isn't just a commodity. It is a meticulously engineered medical tool designed to manipulate the internal ocean of the human body.
And when you lose access to it, you realize how delicate the physiological architecture truly is.
Exactly.
So bringing it all together, the ultimate takeaway from this deep dive is that fluid balance defies simplification. It is not an accounting ledger.
Not even close.
It's this highly dynamic, actively negotiated distribution of water across selectively permeable membranes, protected by microscopic gel barriers and governed by stress hormones.
Whether we are looking at burn resuscitation, the feast trial, or runners crossing a finish line, the evidence is absolute. Blindly pushing more fluid is rarely the panacea we want it to be.
We really have to move past treating the body like an inert container.
Yeah. The human organism is constantly adapting to preserve its core functions, and our interventions just have to respect the complexity of those biological defenses.
Absolutely. So I want to leave you with a final mechanical reality to consider as we wrap up.
Sure.
Right now, without any conscious input from you, your body is managing a microscopic internal ocean. Your pituitary gland is titrating antidiuretic hormone, your endothelial glycocalyx is actively trapping plasma proteins, and your cell membranes are utilizing ion pumps to keep from drying out or rupturing.
It's constantly working.
You are quite literally a walking, self-regulating bag of seawater. And if the brightest minds in critical care have spent the last century repeatedly realizing how dangerously wrong their assumptions were about something as seemingly simple as water and salt, what other fundamental everyday functions of our own anatomy are we currently entirely misunderstanding?